Before we start this video, I would like to make a correction. In the rest of the video you will see 13 here, you will see 13 here, and it should be in fact 14. So when you see 13 here, ignore it. Here it means 14. From the previous lectures we had first the notion of nilpotent operators, and it is important to stress that we defined it like this, that is the operator raised to the power the dimension of the space being the zero operator, but it's equivalent to saying the operator equals 0 raised to some power. There exists some j such that n to the j is 0. We also had from lecture 13 that any complex vector space, so this complex vector space, it can be decomposed as the direct sum of generalized eigenspaces. It's a direct sum because generalized eigenvectors are linearly independent, and we also know that each generalized eigenspace is invariant under T, so we can restrict T to that space and it will be to that subspace. And we also know that T minus the eigenvector minus the eigenvalue when restricted to that space is nilpotent, and so nilpotent properties of being nilpotent will play a role into this game. So not only T minus lambda I restricted to that generalized eigenspace, if we raise this operator to the power n, not only it is 0, but actually we don't need to raise it to the power n. We can raise it to something smaller. It just needs to be this dj, where dj is the dimension here, which, by the way, we call algebraic multiplicity. So the dimension is, if dj is the dimension of the generalized eigenspace corresponding to the eigenvalue lambda j, we call this algebraic multiplicity. And we saw that, well, because these two here are equivalent, it is enough to raise this the restriction of this operator to the power dj to get the zero operator. So all these actors were very important for the lecture of today. These are things we have seen already before, and we also used a lot properties of polynomials, which you can review in chapter 4 if you need. We also used the fact that the space of linear operators on a finite dimensional vector space is itself finite dimensional. In the first part of the lecture today, it was pretty much independent of the rest, and it works for any field f. It doesn't need to be the complex field, using properties of polynomials and the fact that the set of operators, of linear operators on a finite dimensional vector space V is itself a finite dimensional vector space. We defined what is the minimal polynomial of an operator. We gave it a definition, and right after the definition some examples, and I suggest you go back there and check those examples, because definition may be easier to check than going through the proof. I saw that some students, they understood the proof so well that later on they were trying to prove that certain polynomial was indeed the minimal polynomial of a given operator by actually checking the proof and talking about whether t, identity, t squared, etc. are linearly independent, etc., etc. All these things, they're inside the proof. But sometimes it's easier to just check the definition. And the definition, it makes sense, it is well defined, exactly because we proved it. So it is good to look at the definition. And if you were given an operator and you want to find the minimal polynomial, one very important property is that the roots of the minimal polynomial in that field, f, so it can be the real roots or it can be the complex roots depending on what your field is, they will be the eigenvalues the eigenvalues in the field, of course, of that operator. These you can use this because this tells you, at least when f equals c, it tells you what form the minimum polynomial must have. Because on the complex field, a monic polynomial having certain roots, you know exactly what form they have. On the reals, it's more complicated because you can always multiply a polynomial by an irreducible quadratic form, and you will not change the set of roots of that polynomial. And it can even make the polynomial still be a monic polynomial. And last but not least, we also saw that the minimal polynomial is a factor of any other polynomial that annihilates t. Meaning what? Meaning if there is any other polynomial that apply to t, gives the zero operator, then that polynomial must be a multiple of the minimal polynomial. A multiple in the sense that it is the minimal polynomial times another polynomial. Then we moved completely to the world where the field is complex, and then we defined the characteristic polynomial as the polynomial of the form z minus lambda to the power the multiplicity of lambda, where the multiplicity has been defined as the dimension of these spaces, and we know the dimension of these spaces, they add up to n, so the characteristic polynomial has degree n. And we saw the Cayley-Hamilton theorem. In the proof of Cayley-Hamilton theorem, we just had to note basically that not only g of lambda t equals the kernel of t minus lambda I to the n. Of course, this is how you define it, because you don't know yet what is the algebraic multiplicity before you have g of lambda t. But once you have it and you know which dimension it has, then you can replace this by a smaller number, which will be just d, the algebraic multiplicity of that lambda, dj. So we know that this eigenspace, this generalized eigenspace, it is also equal to the kernel of t minus lambda I to a smaller power. And that's why when you apply this characteristic polynomial, which is a product of terms like this, when you apply it to the operator t, you get the zero operator. Because each term like this, when you put t here, and you apply it to the corresponding generalized eigenspace, it will be zero on that eigenspace. And since you are composing many of these, each factor in this composition will ensure that the operator is giving zero for generalized eigenvectors corresponding to any eigenvalue. So that's how we get Cayley-Hamilton theorem. And the connection between minimal polynomial and characteristic polynomial is very subtle and very narrow. And it's basically Cayley-Hamilton theorem says that the characteristic polynomial applied to the operator gives zero, and therefore the minimal polynomial has to be a factor of the characteristic polynomial. But we know much more. Not only it is a factor, but also it has the same roots. So basically the only difference between minimal polynomial and characteristic polynomial is in these exponents here. But here, this, of course, we are talking about now only when the field is the field of complex numbers. Now, as pointed out by some students in the exit ticket, so this whole theory now is adding another algebraic actor into the game, because now we are considering the interplay between polynomials and operators. And some of them mentioned, and I agree, that it's almost hard to believe that an operator combined with its own characteristic polynomial will give the zero operator. Some things I would like to mention is that some students are still saying inner product space, Well, of course, everything we're saying here, it's true for finite dimensional inner product spaces, because inner product spaces are vector spaces, but we're not using this term anymore because we are not using the inner product for anything right now. And maybe one possible misconception that some students may have, I'm not sure, is that the minimal polynomial has to be of this form, z minus a number to some power. And that's not true. The minimal polynomial can be anything. Any monic polynomial can be the minimal polynomial of some operator. It doesn't have to be of this form. So if it's not of this form, which form is it? Well, it will be the product of a factor like this, and a factor like this, and a factor like this, and so on. So it will be a finite product of factors like this, and we can always write all these factors monic. This is an easy way to ensure that the product itself will be monic. Some students pointed out that nilpotent operators were not so important in this lecture. I agree, they were not the central players, but they were important in using this characterization to combine with this property here to get the Cayley-Hamilton theorem. We would not have been able to get the Cayley-Hamilton theorem otherwise. Some students pointed out that we're now using theorems of Honor's linear algebra 1 as definitions and arriving at definitions of Honor's linear algebra 1 as theorems. I have to agree, this is pretty much what we are doing here. I would like just to add to this that in Honor's linear algebra 1 we stated the spectral theorem but did not prove, and we also stated the Cayley-Hamilton theorem but did not prove either. And some students stress that we are defining the characteristic polynomial without making any reference to the determinant. Indeed, the determinant is not needed to anything we have done so far in this Honor's linear algebra 2 course. And finally, some students pointed out that in this lecture we saw finally the notion of generalized eigenspace become much more useful, and that it defines algebraic multiplicity, characteristic polynomial, and allows us to arrive at the Cayley-Hamilton theorem. And I would agree, this is one of the main reasons why generalized eigenspaces were introduced in the first place.